This is question 3 from exam 3. A spring is initially compressed by a 50.0 Newton force, a distance of 7.50 centimeters, from equilibrium by a 7.00 kilogram block of wood. The block of wood is released from rest and slides along a rough surface with a coefficient of kinetic friction of 0.350. The block is not attached to the spring and will slide away. In part A of the question, we're asked to find the spring constant, K. So, when the spring is initially compressed, we can examine the forces acting on the block of wood just before it's released. There is some external agent applying a force on the mass, and then the spring is applying an equal and opposite force on the mass. So the magnitude of the spring force, which we know in magnitude is equal to K times XB, must be equal to this applied force that they give us, 50.0 newtons. So this tells us that the spring constant is equal to the applied force over the compression distance, equal in magnitude XB. So we put in the numbers, 50.0 newtons. We divide by that compression distance, which is 0.075 meters. And the answer is 667 newtons per meter. So once we know the spring constant, that's what it is in any subsequent parts of this example. So in part B, we're to use the energy principle to find the speed of the block at the equilibrium position. This is once the mass is the external force F sub A has been removed, and so the mass and spring can go back to the equilibrium position. And so there are two forces acting on the mass as it moves to the equilibrium position. The force of the spring and also the friction force. So the energy principle can be stated: work by external forces is equal to the work done by the spring plus the work done by the friction. The work done by the spring is going to be equal to 1/2 K times the change in distance squared, which is just going to be XB squared, minus F sub K times XB. And that's going to cause a change in the kinetic energy. Delta K, which is equal to 1/2 mv squared. So its initial kinetic energy is 0. So we are to solve for the velocity. So we can rewrite our equation as 1/2 kxb squared minus mu sub k mg times xb is equal to 1/2 mv squared. If we go ahead and solve for this, the work done by the spring, that's equal to 1/2 times K, which we found to be 667 newtons per meter, over the compression distance squared, which is 0.075 meters all squared. We find that the work done by the spring is 1.876 joules. The work done by friction is equal to minus mu sub k, which is 0.350, times the mass, which is 7.00 kilograms, times g, 9.8 meters per second squared, times the distance, 0.075 meters. And I calculate that as minus 1.801. So 1/2 mv squared is equal to the difference between the work of the spring and the work of the or the sum of the work of the spring and the work of the friction, and that's 0.075 joules. So sum for the velocity, 0.075 times 2 joules in the numerator over the mass, 7.00 kilograms. I get 0.146 meters per second. Then in part C, use the energy principle to find the distance the block will travel before coming to the rest, i.e. the total distance from the starting position. Well, you can do this two ways. You can start with the mass at the equilibrium position, where all of its energy is kinetic energy, and then it comes to a stop. So there's a change in kinetic energy due to the friction acting on that distance. So then the work external in this part is just equal to the work done by the friction times the distance it slides from the equilibrium point. And that's equal to the change in the kinetic energy, which is equal to minus 1/2 mv initial squared, where v initial we found to be 0.146 meters per second. So I'm going to let you go ahead and solve for that. And when you do, you find that the distance is 0.312 centimeters. So if you want the total distance, you have to add that d plus the starting point distance, which is 0.075 meters. And when you do, you get a total distance of 7.81 centimeters. Alternatively, you can start with the block of wood compressed in the compressed position. So in that case, its initial kinetic energy is 0, and the final kinetic energy is 0. So the work that's being done is the work done by the spring plus the work done by the friction over the total distance. So this is the work done by the spring, which is 1/2 K xb squared plus the work done by the friction, which is minus F sub K times the total distance. And that's equal to the change in kinetic energy, which is 0. So now the total distance is equal to 1/2 K xb squared over F sub K. And if you use this method, then you'll get the same total distance of 7.81 centimeters. And that concludes this video.